Welcome my friend. So, welcome to my next lecture. So, in my last lecture I talked about the notion of Riemann integrable for a functions defined on say bounded rectangle real valued functions. Okay. So, then I have defined the notions of upper sum, upper integral, lower integral, and then I defined the notions of what is called Riemann integrable. Then I discussed two examples, a constant function which is Riemann integrable, and another function I have discussed which is like that kind of functions you have seen in your single variable calculus, like it is taking some value 1 which is varies over rational and irrational, it is taking something. It's a very bad function, and that functions I have discussed that function is not Riemann integrable because I have calculated the upper integral and lower integral explicitly, and there it will upper integral it will give you one value, lower integral it is giving some other value. So, therefore, my function is not Riemann integrable. So, that is one of the way I have defined. Now, I will define in terms of Riemann sum, and then once I have the notions of Riemann integrable, then I will talk about what is called iterated integral, and then Fubini's theorem will automatically come into the picture to talk about the equality of the iterated integral along with double integral, and then you will have the notions of change of variables, and at the end I will talk about some applications. Okay. So, now before I start, of course, I say that now I want to define my Riemann integral in terms of Riemann sum. So, before that I need what is called refinement of the partitions or refinement of a mesh. So, what is that? So, suppose you start with a what is called bounded rectangular region. So, let R be a bounded rectangular region, that means R is of this kind of form that I already explained. Now, you take a partition P. So, partition P means you take a partitions of your interval AB and partition of your interval CD, take a cell Rij which is I already discussed, which is nothing but the cell xi minus 1 comma xi cross yj minus 1 comma yj. If this is my cell or this is a mesh of R or partition of R, the points or vertices xi yj or I from this and j from 1 up to m is called the mesh points or grid points. So, now look what is the point. So, this is xi and yj, and these points actually if you see this is a point in the cell Rij, because what is Rij? This is nothing but xi minus 1 to xi cross y j minus 1 to yj. Okay. So, therefore, xi is sitting here, yj is sitting here. So, therefore, this is a point. So, this point is called the grid points of the partitions P of the partition or the mesh P. That is exactly I have written. The points or vertices xi comma yj, I from 1 up to n, j from 1 up to okay, there is a typo, this should be n, yes. Is called the mesh points or grid points. Okay. Now, I want to define a refinement. A mesh Q is said to be a refinement of the mesh P. Okay. If each mesh point of P is also a mesh point of Q. So, that means I have a rectangular region, I have a partitions. So, I am doing the finer partition. So, that means very pictorially if I say for example, this is my square. So, suppose this is my partition, okay, I am taking two things, that is this is one partition, right. So, what are the cell? So, this is one cell, this is one cell, this is one, okay. So, this many cells are there for partitions of this rectangular bounded rectangular region. Now, what is the refinement? So, I want a further partitions of my cell Rij. So, suppose this is my cell Rij, okay, of the first partition. Then I want a more finer partitions of my interval or rectangular region. How to do that? What you have to do? So, now look at this cell Rij, okay, you take a partition there itself. So, that means you take a finer partition there also. I mean, consider this, okay, and do the all cells Rij. So, that means this. Now, look, so if suppose this is your Rij earlier, now look, I have further partitions. So, I make sub partitions of my earlier Rij. Now, if I consider this each cell of my original interval, so this is, so this, if this is my cell, then this is a finer partitions of the given partition P. So, what you have to do? So, you have a bounded rectangular region, you take one partitions and you take further partitions of your cell Rij, and if you take the partitions of your interval Rij for I running from 1 up to n and j running from 1 up to n, this together will give you finer partitions, and that I am talking about as Q, and that is kind of way of understanding, but how to write it mathematically, that exactly I have written here. So, a mesh Q is said to be a refinement of the mesh P if each mesh point is P is also a mesh point of Q. So, that is all. So, the grid point, so that means if I have a grid point, so if I take a grid point here, that is also a grid point of this small one. Na? So, that exactly x, I, y, j, if I take the any point in the boundary, this boundary points, this is also a mesh point of your finer partitions Q. Okay. In other words, what I am trying to say is that in additions, so of course, all the mesh points of your earlier partition P are mesh points of Q, that is okay. But look, this is another point, you have another point. These are extra mesh point which were not a mesh point of your partition P. In other words, in addition to all mesh points of P, the refinement mesh Q may have some more mesh points, and it is expected, right, because you have Rij, we take another partitions of your cell Rij, and you have done it for all Rij's, I running from 1 up to m and j running from 1 up to n. So, of course, the partitions like the xi, yj point, these are the mesh point of your finer partition Q, that is okay, but at the same time you have more number of points inside your cell Rij, and these are the actually what is called more mesh points corresponding to the partition Q and not in P. So, that means in Q you will have more number of mesh points compared to the earlier partitions P. That is exactly I have written. In addition to all mesh point of P, okay, mesh point or grid points I already said, which is xi comma yj. Okay. If this is the case, then the refinement mesh Q may have some more mesh points. Okay. So, in other words, in real case, in the case of single variable calculus, what is that? It is very easy to understand. Suppose this is my interval A to B. Okay. Suppose you are having a partition say P. Suppose this is my interval xi minus 1 xi. Okay. And then suppose this is my partition P. If I have a partition P which is x0, which is exactly equal to A, x1 up to xn is equal to B, then what is the refinement of my partition? You take a further subpartitions of your interval xi, this is true for all I. Okay. And if I take this point as a partition points, this is the points, then I will say that this Q is a refinement of P. So, that means you have to involve more points in your partition set P. So, earlier you have how many points? Only n plus 1 points, x0 up to xn. Now, you will have more number of points because I am subdividing my interval xi minus 1 to xi more number of points. So, that means the refinement has more number of points. So, similarly, you will have the in case of R2 you will have more number of grid points. That means once I have a partition P, you just go to the your cell Rij and take further partition. That means you have more number of grid points. Okay. Once I have the notions of refinement, that is called the refinement. If Q has more number of what is called mesh point, that means it is called the refinement of your earlier partitions, or you take a partitions, go to the cell Rij, make a further partitions in that square, and it is true for all I and j, and take all those points. This is called the final partitions of the partition P. Okay. Once I have that one, then let f be a function which is bounded. Okay. R is a bounded rectangular region. Suppose I am starting with a bounded functions. If Q is a refinement mesh of the mesh P, that means if Q is a refinement of the partition P, then what will happen? Two conclusions I had drawn. One is the upper sum will what? Upper sum will decrease and lower sum will increase. And in other words, norm of your partitions is lesser equal to norm of the given partition. Suppose you start with the partitions P, if you take the refinement of your partition P, that means the refinement one, that means Q, the norm of the partition is lesser equal to norm of P. Now, it is become quite clear from the context why its norm or upper sum or lower sum will increase and decrease, that is clear, because how you obtained or what is the definitions of the refinement partitions of the given partition P. Given partition P, if you have a kind of some sub rectangles are there, or one of the cell is Rij, and what is the refinement? You are taking more sub rectangles of the cell Rij, that means you have your area of the rectangle decreases, right. So, that means earlier you have the big one Rij, now you have again small, because you are taking another kind of partitions of your interval Rij, of your rectangle Rij, and that will give you the length or area is little less, of course lesser than Rij. So, that means if I take the supremum and infimum, of course in that case u of Qf, that means that will decrease, right. And similarly, what is your LPA, that means that will increase. Okay. So, that is why this is quite clear, because you are making your partitions of your subcell Rij in finer partitions. Okay. and of course the norm will also it is also because area will decrease or diameter will decrease, because if I have the partition P, whatever the kind of square will be there, that is denoted as Rij. If I consider the length or diameter, and if I take the finer partition, because I am taking more subdivision of my cell Rij, of course the subrectangle's area will be less. So automatic then once the area of the subrectangle is less, so therefore length of the partition also less or equal to the norm of the given partitions. So therefore if I have a bounded functions, if I have a partition P, if I take a finer partitions, my upper sum that will decrease and my lower sum that will increases. So therefore the question is, at some point of time if I take finer and finer partitions, so upper sum will decreases and lower sum will increases, and of course lower sum is less or equal to upper sum, because upper sum is associated with the supremum of my functional values xy running over this cell Rij, and lower sum associated with the infimum of functional values xy running over that cell Rij, and of course infimum is less or equal to supremum. So therefore it is easy to conclude that lower sum is always less or equal to upper sum. So now if I take finer and finer partitions, so one hand lower sum increases and upper sum decreases, so at some point of time they should be equal, and it is indeed the case. If my function is nice, this function, that upper sum and lower sum will be same, and that is give the conditions for the Riemann-Darboux integrability. So now I want to talk about the Riemann sum, those notion of Riemann sum. Okay. So that means you start with a function f which is defined on a bounded rectangle subset of R2 to R. Okay. So what you have to do, once we have a bounded rectangle, you take the partition, and I am starting with a partition P which is Rij, I running from 1 up to n and j running from 1 up to n. I think now it is clear, because m stands for the partitions in the interval AB, and n stand for what is called the partitions of the interval CD in the y axis. So now it is quite clear, indices I and indices j. I running for the partitions of the interval AB and j running for the partition of the interval CD. So you have a bounded rectangular region, you have a partition P whose ijth cell is I denoted as Rij, and that you know what is Rij. This is xi minus 1 comma xi times yj minus 1 to yj. What you do, choose any point xij from your cell Rij. In other words, I am drawing a picture here. Look, what is this? This is for example R23. Okay. So this is the cell R23. What you have to do is just take any point from here. This is called x2, x2 star and x2 and y3 star. Any point. So you take Rij, take any point which I denote it as xi star, yj star. It could be a corner point, could be an interior point. Okay. And then perform or define a Riemann sum. What is that? Riemann sum is nothing but what you do, you just take the functional value at the point xi star, yj star, that means the point you are taking from your cell Rij, evaluation of functions at that point, times the area of this rectangle Rij, and then you sum it up, I from 1 up to n, j from 1 up to n. In the single variable case, you have exactly done the same things, right? You have a functions f defined on closed interval a to b to r. You take a partitions of AB, consider the sum interval xi minus 1 to xi, take a point sum j or ji and perform the Riemann sum. That means sum over I up to 1 up to n f of ji times xi minus 1. This is called the Riemann sum. If partition goes to 0, whether that limit exists or not. Exactly I am doing the same thing. This time I have a what is called rectangular region. I am taking a partitions. I am considering the cell, subcell, subrectangular cell Rij, taking a point xi star, yj star, making a Riemann sum, or what is that? Sum over I, sum over j, because these many sub-rectangulars are there for my given rectangular region, or the partition is there, partition points are there. Then what you do, take a point xi star, yj star, evaluate my functions at that point, hit it by the area of this rectangular region Rij, and take the sum. This time we will have double sum, because I am taking partitions in R2, because in x axis as well as y axis, this is a Riemann sum. Now next slide I will talk about, okay, if now norm of the partition goes to 0. Now norm of the partition goes to 0, what do I already discussed what is the norm of my partition in the context of the R2 sense, okay. If this is true, then what will happen in the limiting case? Okay, so that exactly the case. So now Riemann sum what? So given a partitions, Riemann sum I am denoting as S P of f. So given function f, given a partition P, I will have a what is called Riemann sum, and it will give you some value. Okay. So now I want to say, okay, if partition goes to 0, or if I take finer and finer partition, then what will happen? Okay, that's exactly the one, Riemann sum and Riemann integral. Look, what I said is that, okay, I am saying that suppose there exists a real number L, suppose there is a real number L, for each epsilon, if there exists a partition P of my rectangular region R such that if this is the true, what is this? What I am saying is that, okay, suppose there exists a real number L, suppose you have a real number L, whatever epsilon, for each epsilon, if there exists a partitions, given epsilon, if there exists a partition P of R such that the distance between SQF, that means Riemann sum corresponding to the partition Q and L less than epsilon for every refinement Q of P. So, that means I am saying that, okay, suppose you have a L and which has the following properties. What is the property? Property is that whatever epsilon I am considering, for any epsilon, there exists a partition, I will have the existence of one partition P such that whenever I am taking any refinement of my given partitions P, the corresponding Riemann sum SQF and L difference is less than epsilon. If this is the case, then I will say that my integral or Riemann W integral exists. So, that means if that L satisfies these properties, that means whatever epsilon I can take, that will give you one partition such that if I take any other finer partitions of my given partition P, the distance between the Riemann sum corresponding to the refinement partition Q and L, which is less than epsilon. If this is the case, then I will say that my Riemann W integral exists and the value is exactly equal to L. Okay. So, that is one. So, now this is same as I said, if norm of the partition, refinement means what? I can add more and more points in my earlier partitions and you have a refinement. Add more and more points. The more points you will add, the length of the corresponding partition goes to 0, because you are having very small and small and small and sub-rectangles, and area goes to 0 or diameter goes to 0. In other words, length of your partition goes to 0. So, in other words, I have written in note, if f is integrable over R, then integral, that is Riemann W integral, which is nothing but the limit of my Riemann sum if norm of Pn goes to 0. Okay. So, that means you, if given a partitions P, what is called Riemann sum, if the norm of the partition goes to 0, then if the my function is Riemann integrable, then this limit is nothing but the value of the Riemann integrable. And that is exactly the limit exists, that means it's actually this is the, if there exists a number L which has the following properties. What are the properties? For any epsilon, if there exists a partition P such that whatever refinement I am taking for this partition P, the distance between Riemann sum corresponding to the refinement partition Q and L, which is less than epsilon. If this is the case, it is actually saying that my function is Riemann integrable. In other words, double integral over R f x y exists and it is exactly equal to the value L. So, if my function is Riemann integrable, which is nothing but the limit of the Riemann sum as partition goes to 0. So, look, I have written, so this is the Riemann integral, which is nothing but limit of norm of Pn, that means taking finer and finer partition means norm of the partition goes to 0 for any sequences Pn which norm goes for. So, this should be true for any partitions, sequence of partitions Pn. So, if I have a sequence of partitions whose norm goes to 0, then the limit of the Riemann sum is exactly equal to the Riemann W integral of f over this bounded rectangular region R. So, that is the definition. Okay. Okay. So, I think I have written in another way the same whatever I have discussed, that I put it as a theorem. It says that there exists a real number L for each sequence Pn or each meshes, that means each partition you have, suppose there exists a real number L and suppose you have a sequence of partitions Pn of R such that norm of the partition goes to 0 as n approaches to infinity. It happens that suppose this limit exists, that means if limit n approaches to infinity, the corresponding Riemann sum S associated with the partition Pn for the function f, suppose this limit exists and suppose this is the value is L, if and only if my Riemann integrable or Riemann W integrable of f is exist and the value is exactly equal to L. Okay. So, now this is another way of defining Riemann W integrable. So, what you have to do, suppose you are starting with a nice functions, starting with a bounded rectangular region, take a partitions, form a Riemann sum. Now, if you have a partition or if I have a partition, take a finer and finer partitions, if the norm of the partition goes to 0, then if suppose if I take norm of the partition goes to 0 corresponding to that partition, you make a Riemann sums. If the limit of the Riemann sum exists, that means if limit n approaches to infinity, S Pn f which exists, and if suppose the value is L, then I will say that my function is Riemann-Darboux integrable. That means double integral over R f(x(y) dA exists, and it exactly equal to the value of the limit L, which is nothing but the limit of n approaches to infinity S P n f. Okay. So, that is another, that is in terms of the what is called Riemann sum. Okay. So, if from a Riemann sum take a partition goes to 0, if the limit exists, that means I will say that my function is Riemann-Darboux integrable, and what is the value? Its value is nothing but the value of the limit. One corollary. So, if my function is positive, okay, then this gives the volume of the region bounded by R and the graph of f. So, now as I said, since if I am functions from R2 to R, if I go for R3 to R, then it is very difficult to draw a picture. However, if I have a functions from R2 to R, then what will happen? So, the graph will give you some kind of picture in R3, and you will have a region, you have a graph of f and you have a region. So, now you can visualize, that means it will give you some kind of region, and in fact that the Riemann-Darboux integral will give you the volume of the region. For example, in single variable case, what is going on? Suppose you have a very nice function, okay, suppose this is my a and b. So, you know that what is my, suppose this is my function. So, that means integration a to b f(x) dx, what it is? This is nothing but the area of this curve bounded by the x axis a to b. So, that was the what is called geometrical significance or applications, you can say. So, if I have a nice functions, the integral of the functions f, if my function is very nice, that means integration a to b f(x) dx, which is nothing but the area of the graph of f, and you have the x axis, that means the interval of the region in which you are integrating your function f. So, this is nothing but the area. Now, in the context of functions from a b to r, or say if I have R2 to R, so if I have a functions from say a b cross c d to R, in that case what is the meaning of double integration a b cross c d f, and suppose your f is positive and very nice, okay, then what will happen? So, that means in that case you will have a 3-dimensional picture, right. So, what is the graph of f? It will give you some kind of things, okay. So, I am very bad at, and suppose you have a kind of square. So, that means it will, I am very bad at picture. So, that means you will have some surfaces, and in the xy plane you have a that what is called bounded square region. So, what we will have? So, you have a square region and you have a surface. So, this is nothing but the volume. So, I think let me try to draw. So, suppose what is called, so suppose this is your square region, okay, and suppose you have a graph. So, this is my graph, okay. So, what will happen? This. That means that the volume I will have. That means it is the bounded by the graph of f and the region bounded by R. So, that means this is the one. So, it will give you the volume of this region. That is what the interpretations, and it is expected because I have just extend the exact the same concept of Riemann integral for R to R to the context R2 to R or some rectangular region to R. Okay. So, there is another theorem I have discussed. If my function is continuous, as I said, if my function is nice, means I am talking about the continuous functions. If I have my function is continuous, then f is Riemann integral over R, where R is a bounded rectangular region. This is kind of some sufficient conditions. If my function is continuous, then my function is Riemann integrable on R. Okay. So, just I will talk what is called some properties of double integral, then I will stop here because next class lecture I will talk about what is called iterated integral. Okay. What are the properties? So, like in the single variable calculus, the notion, if I have the notions of Riemann integrable functions, then you know. So, what is that? So, that means if I hit it by some scalar in the functions, then that scalar will come out. Okay. So, that means the integral over R k f, which is nothing but k times integral over f times dA. If I take the sum of two Riemann integrable functions, that means f plus g times dA, which is nothing but they will split it up. That means integral double integral of f plus double integral of g. Okay, some kind of linearity actually. If my f of x is lesser equal to g of x for all x in the region, rectangular region, that means the corresponding value of the double integral is dominated by the value of the double integral g. Okay, so that kind of ordering relation it follows. this is another important, if R is subdivided into two simple regions R1 and R2, but there is a catch is that note that the only overlap between them will be a common portions of the boundary curve. Okay. So, that means something like that. So, that means if this is the case, of course, you will have this kind of things here, not an issue. Okay. So, that means suppose I have a full region and suppose it is subdivided into two simple regions R1 and R2, there is a remark here that note that the only overlap between them will be a common portion of the boundary curve. This is the boundary curve, this is the boundary curve. Okay. Then what will happen? The double integral f of R, which is split it up into R1 and R2. Okay. Like in the Riemann integral in the single variable. So, if my modulus of f, that is mod functions, that means x y goes to modulus of x y, this is the functions. If mod f is Riemann integrable, then this kind of inequality is true. That means, you just make the perform the double integral of f, and if I take the absolute, which will be dominated by the double integral of your functions modulus of f. So, if my function f is integrable, Riemann-Darboux integrable, along with that modulus of f is Riemann integrable, then this is the case, it is true. That means, this kind of domination is there. And in particular, if I take f is the constant function 1, that means you will have, so right, if I have constant function 1, so that means the integral is nothing but the area. So, when I will talk about the applications part, it will be clear, that means of course, area and volume will be there. So, these are the few properties of your double integrals, okay, like in a single variable calculus you are familiar with, similar kind of things it will be true. Okay. Kind of linearity, scalar multiplicability, or ordering part, or if I have region is divided into two, that means that they split it up, and if mod of f is Riemann integrable, then this kind of inequality is true and at the area. I think I should stop here right now, okay, because in my next lecture I will talk about the notions of iterated integral, like as I said, in the context of limit you will have the iterated limit. So, now iterated integral also similar way I can think about, since I am dealing with a function, again I am in R2 to R setting. So, if I have a function from R2 to R, if I fix one variable, now I can think about is a function from R to R. Now, I can have a notions of Riemann integral. So, therefore, you do integral for keeping one variable fixed in one variable, and then you perform the integral in other variable, and vice versa, another way around. So, that means you have two iterated integrals will be there. So, the question is there any relations with the existence of iterated integral and the double integral I have just discussed. And of course, you will see Fubini's theorem will play a role to talk about that. I think I will start with those concepts in my next lecture. Thank you.